Alrighty, guys. This is going to be the last video on inverse trig derivatives, largely because this is still 3.5. I've already done 5 videos on implicit differentiation as such, and then this will be the third one on inverse trig. So that's a total of 8 videos for 3.5, and quite frankly, I think that's enough. I think I'm going to move on after this. If you have any particular questions, I can of course entertain those on a piecemeal basis. But let's go ahead and jump right in with a couple of nastier problems. That's always the best way to ensure that we actually understand the material, right? I never introduced really nasty ones just for the sake of watching y'all groan, although that was always a nice little added benefit. It was mainly when you get to the point where we can actually do this with no problem, then the more moderate ones, the easier ones, sort of pale in comparison and wind up, that basically is an indication that those are at that point they wind up being instinctual. Okay. I'm going to go ahead, this is the way it's actually written in the book. I don't particularly like this. I would rather not have to deal with the 1/2 sort of lingering out in front, and I'd also like an excuse to go ahead and write that original radical as a fractional exponent. That changes the 4 right here into 2, and then either inverse sign or arc sign, whatever your preference is, you know mine. But I like to go back and forth just to make sure that you remember that they're synonymous. But in this first one, of course, we're going to have to deal with product rule. So let's go ahead and do that. So we have u times the derivative, that's supposed to be 1/2, of v, okay, plus the derivative of u times v, plus 2 times the derivative of, so that winds up being 1/2 square root of 1 minus x squared over 4. Now that looks ugly, and it should, okay? But you can multiply through to actually simplify that. Let's do one round of simplification really quickly. Now notice that this -2 right here cancels with one of these 2's, okay? So we'll go ahead and cancel that 2 with that 1/2. Remember that that leaves a negative though. Don't get rid of the negative, okay? And I recognize the fact that, I mean, you could scratch out the 2 and the 1/2. That might actually help us so that we have fewer things to distract us as we're moving forward. And this first one winds up being x squared over 2 times radical 4 minus x squared. This one winds up being radical 4 minus x squared over 2. And this one winds up being 1 over the square root of 1 minus x squared over 4. Okay, it's x squared over 4 because the x over 2 was squared. Now we can actually multiply this right here by 2 over the square root of 4. And if I do that, that term transforms and becomes 2 over the square root of 4 minus x squared. Okay, I'm going to go and do it on the same line so I don't have to recreate it. At this point, we can simplify. We simply have to get a common denominator, okay? Well, in order to get a common denominator, this first one doesn't require anything additional. This second one winds up needing to be multiplied by the radical over itself. And this last one needs to be multiplied by 2 over 2, okay? And so what happens here is this winds up being 8 over 2 times 4 minus x squared, because the x squared and the negative x squared cancel each other out, right? Oh, actually, no, I totally forgot. I forgot to carry the negative right there. So that winds up being 8 minus 2x squared. So that winds up being 4 minus x squared over radical 4 minus x squared. And therefore that winds up being 4 minus x squared. Unless I made a mistake somewhere. I don't think I had. But you get the basic gist. And this was another one like the one that we had in the last one, where one term had arc sine and the other term had radical of 1 minus x squared. And of course, they wrote those that way on purpose so that there would eventually be some cancellation. Now, let's go ahead and do another one kind of the same variety. Winds up being a little bit of the same sort of tune. And so let's say I have that. Well, I know that y prime is going to be 1 over 1 plus x squared. This, however, is going to require the quotient rule. So I have the bottom times the derivative of the top minus the top times the derivative of the bottom. All of that over the bottom squared. Well, that winds up being, well, this first one doesn't need any simplification, but this second one certainly does, and that winds up being 1 minus x squared over 1 plus x squared squared. You could go ahead and change this first one by multiplying it by the denominator over itself in order to ensure a common denominator, at which point you get 2 over 1 plus x squared squared. And that would be the derivative of that sum function right there. You know, cleverly crafted so that it would actually come out to something nice and neat and tidy. I think that kind of brings us to the end of that sort of thing. I would like to, at this point, do a couple of tangent line problems. Let's go ahead and do a tangent line problem that's, you know, pretty straightforward. Okay, so we have the order pair 1/2 pi over 4, and if you want to, you know, ensure that this actually is, you know, a point on the curve, you could actually put in, you know, 3 times 1/2 times arc sine of 1/2 and see what that equals. Now, arc sine of 1/2 is going to be what? It's going to be pi over 6. Pi over 6 times 3/2 is indeed pi over 4. Okay, so check. That order pair actually does occur on the curve. Okay, but we need the tangent line there. So we have the point, and in order to get any line, of course, we now need the slope. Well, we need to take the derivative then, because this derivative is the slope function. So we have the first times the derivative of the second plus the derivative of the first. And let's go ahead and put brackets around that like we usually do. The derivative of the first, which is 3, times the second, arc sine of x. Which gives us 3x over the square root of 1 minus x squared plus 3 arc sine of x. Well, if I go ahead and evaluate y prime of 1/2, okay, I recognize that that's going to give me 3/2, and then of course this is going to be the square root of 3/4, so that's going to be root 3 over 2. Plus 3 arc sine of 1/2. Well, arc sine of 1/2 we've already determined is going to be pi over 6. So this is basically, this winds up being 3 over root 3. Well, 3 over root 3 winds up being root 3. And 3 times pi over 6 is, of course, pi over 2. So that winds up being our slope, as nasty as it is. So that gives us a tangent line, which is y minus pi over 4 is equal to root 3 plus pi over 2 x minus 1/2. And, you know, just hope and pray that you're not required to put that into slope-intercept form. But that would basically be it. Now I have one more tangent line problem because it's actually inverse trig and implicit. So it's like 2 layers of implicit. How much fun is that? And then I want to go back and I want to explain a problem that I did in the last video. I made a split-second decision not to explain it to you at the time, but I think it'd be worthwhile to go back and do just by way of a reminder. So arctan of x plus y is equal to y squared plus pi over 4, and we're going to get the equation of the tangent line at the point 1, 0. Okay, well, if we take the derivative of arctan using our formula, but recognizing that it's also implicit, I know that arctan of stuff is the derivative of stuff over 1 plus stuff squared, right? So let's do 1 plus stuff squared first, and then we need to do the derivative of this with respect to x. So that just winds up being 1 plus y prime. This one is 2y times y prime plus 0. Okay? Well, let's go ahead and let's do 1 plus y prime, and we'll do 1 plus, actually let's put brackets right there, x plus y squared times 2y y prime. If we go ahead and do 1 plus y prime and we distribute that, we get 2y y prime plus x plus y squared times 2y y prime, and we can actually, as nasty as this is, gosh, this is a nasty problem, isn't it? Well, let's go ahead and see it through to the end since we've already started. There probably was a way to sort of preemptively simplify that, but we'll just sort of pretend that it wasn't there. So that winds up being 2y plus 2y x plus y squared minus 1, or y prime is equal to 1 over 2y plus 2y x plus y squared minus 1. Now, the great thing about this is the fact that it's a very easy ordered pair, right? It's the ordered pair 1, 0. Okay, so 0 go in for all the y's, okay, which means that this term and this term go to 0, so the slope is just negative 1, and that gives me y minus y1 is equal to m times x minus x1, or y is equal to negative x plus 1. That right there is my tangent line. Now, I want to go back and discuss one of the problems that I'm going to go ahead and, actually, you can go back and, rewind on the video and pause it if you want. I had the problem y is equal to arc sine x plus arc cosine x, and the derivative wound up being 0. Well, we've seen a derivative equal to 0 before. What does a derivative equal to 0 imply? Well, it implies that this is actually a constant function in disguise. And so I want to talk about that real quick, okay? This is a constant function in disguise. So let's go ahead and do that. So let's go ahead and take the sine of both sides, being very careful not to actually take the sine of each term individually, right? Because you cannot distribute sine to these terms. It's not a quantity. But all of a sudden, this looks like sine A plus B, which we know is sine A cosine B plus sine B cosine A. Well, when you take sine of arc sine, that's obviously x. When you take the cosine of arc cosine, that's obviously x. When you take the when you set up the triangle right here, you take the sine of arc cosine, you wind up getting the square root of 1 minus x squared. And if you don't believe me, go ahead and do it yourself. And the same move when I do cosine of arc cosine. So this winds up being x squared plus 1 minus x squared, or 1. So sine y is equal to 1, so y is equal to arcsine of 1. Now arcsine of 1 is pi over 2. None of this was taking the derivative. This was actually just simplifying and recognizing through a little bit of effort that y is equal to pi over 2. This right here was a constant function in disguise, which is why when you did it the long way, you wound up finding that y prime was equal to 0. So, you know, some of you probably turned off the video when I started doing that, and that's fine. Those of you that made it to the end, you know, I appreciate it. That brings us to the end of our videos on inverse trig. I will go ahead and I think I've already made 1 or 2 of the ones on logarithms, and I will try to get those posted soon. Bye.